are filming simultaneously. Okay? If you've ever thought about how much data comes from one of these video cameras, and now think about processing 100-fold the amount of data, huge amounts of data. Okay, so camera arrays. So here's an example of a camera array. Each of these is a camera, the size of that camera. This is the Stanford camera array. And what it acquires is actually in this case, a 4-dimensional hypercube. That's a cube in more than 3 dimensions of data. Why is it a 4-dimensional hypercube? Well, because each camera, how many dimensions does each image have? 2. And then there's how many cameras? They're laid out in a 2D array. So we have a 2D array of 2D cameras with 4-dimensional data. So now just think for a second. 1,000 pixels by 1,000 pixels in each camera. 1,000 cameras by 1,000 cameras. That's how many pixels? 10 to the 12. A lot of pixels, right? Forget ever trying to load that onto your desktop computer and do anything with it. Okay? So it's very hard. And Dr. Go's working on, you're doing plenoptic stuff. So it's very exciting, but very large amounts of data. So here's our cheapo array. You could build one of these here. Very, very simple. It's just a selection of cameras that are connected by FireWire to a single computer. And then we simulate multiple cameras in the second dimension. Right? You see this is 1 dimension. By basically having a turntable and spinning the object on a turntable. Just like the Matrix. Okay? And at Rice, and other people like Mingo and a lot of other people are working on algorithms for doing rendering of these virtual views, being able to use this for identifying objects, okay, from this 3-dimensional views and other problems. And I think I will show you a example. Let's go to the example. So here's just a student project. This is something you could do. You build one of these arrays. Big camera array. And it's just about, you'll see what it is, an object. And we're spinning the object. And we acquire the data of the object from all possible angles. And then what we can do is with a joystick, choose a view that we want to fly by the object. So we acquire a whole bunch of pictures, but then we say, oh, I want to go by like this. And we can simulate this kind of view. So here's just the example. So none of these, this is not the way that we acquire the data. This is actually defined by the user, and then this is a virtual flyby of this particular sprite can. Right? You see it's very low quality, but it definitely shows you the idea. And things have improved 100-fold over the last few years about how well you can do this kind of thing. Okay? And the first place you're going to start to see this kind of stuff is in like the Xbox, PlayStation, all of these kind of things. In fact, the world's most sophisticated signal processing computers are game computers. Okay? And there are actually people out there who design supercomputers by installing Linux on a PlayStation or an Xbox and then having an array of thousands of them. Okay? Very, very, you should do this here. I mean, yeah, that'd be very, very cool. This is very inexpensive. You get old ones that people don't want anymore, and you build a big array of them. Very exciting. Okay. This is the last name, the one I'm going to talk about, which is very similar, but this is the idea of what will happen in the world when we will have sensors everywhere. Okay? Sensors everywhere. Imagine having an environmental problem where you have an oil well off the coast of Vietnam near Ha Long Bay, and you want to protect Ha Long Bay, but there's an oil spill from an oil tanker. Well, imagine a world where it varies already, actually. A helicopter, you can fly a helicopter over and drop out hundreds of little nodes, and these nodes can sense whether they sense oil or not. They can communicate amongst each other, and they can send information through a satellite back to Hanoi, where you can make decisions about which way the oil is moving. Okay? This kind of technology is here today, so it's pretty exciting. So the idea now is everybody knows what a microscope is. What's a microscope? see very small things in a very localized way, right? Into one cell of my body, right? So what a sensor net is the exact opposite. It's a macroscope. So instead of seeing tiny things at a little tiny scale, the idea of a macroscope is to see huge distributed phenomena, like oil and pollution levels everywhere along the coast of Vietnam or coast of the United States. Okay? So it's basically signal processing, but now on a huge scale. Okay? And there are clearly many reasons why you might want to do this. To sense environmental conditions, pollution, sound, vibrations. You might have fires, and you want to sense where the fires are moving, etc. Okay? So what we've seen in the last 5 years is an explosion of really cheap, what are called sensor nodes, or motes. Okay, these are much bigger than they really are. They're all about the size of your thumbnail, or bigger, or 4 thumbnails. They're very small. They currently cost about $100 US, but within a few years they'll cost $1 US each. Okay? And they'll be equipped with things like temperature sensors or gas sensors, cameras, okay, little cameras, or pollution sensors. And you'll be able to deploy these everywhere. Imagine putting 10 inside this room, right? Cameras in this room so that you can monitor what's happening, so that the professor can know how many students actually showed up in class, right? Etc. Right? Okay, so there's, let me just say, security is a big issue here too. How do you make these things not be used for malicious purposes? But I'll talk about that. Okay. So the big interesting issue here is it's a, we talk about DSP, and we talk about DSP is sampling and then computing. The big thing with sensor nets though is we deploy a network over some region like a city, and somehow we have to harvest the data out of this network. We need to get the information out. And that's going to require some kind of communication, right? Because these are not going to be connected by wires. They're going to be battery powered, and they're going to be interconnected by wireless, like your cell phone or like your Wi-Fi system. Okay? So these sensor nodes have sensing on them, they have computation on them, they have signal processing on them, and they have communication and networking abilities. Okay? But the critical thing is, if you just think for a second, it takes many, many, many fewer joules or battery power to compute on a bit locally inside one of these systems than to communicate a bit. Okay? Communication is extremely expensive for battery power. Computation is actually very cheap. So what this pushes the world of sensor networks toward is the idea of what's called distributed signal processing, where we don't try to just harvest all the data to one place, but try to actually take everything you're learning about in this class and figure out how to do it in a distributed way. Very challenging, but very important. Okay? So one example of this, I'll just illustrate an example, is distributed compression. Okay? So, I already said, let's say that we have a bunch of microphones. Each of you has 2 microphones, your ears, right? Well, let's say that I'd like to transmit out of this sensor net. Each of you is a node in the sensor net. The sound that's heard at the various different places inside the room. Okay, so how many of you are here? 50? From 50? 2 ears per person, 51, 102. Okay? So there's 102 sensors. Okay? So what I want to do is get 102 signals out of my network. Okay? Let's say that each signal is 100,000 points long, and I have 8 bits per point. How many bits total do I need to send out of the network? You're the computing guy. How many? 8 bits per point, 102 signals, 10,000, a million points long each. So 800 million. Okay, so we need to get 800 bits out of this network in order to get about a few minutes of sound.